Okay, we're going to look now at the graphs of motion. In other words, graphs that you draw that depict how an object is moving. First question to be asked is why? What do graphs of motion do for us? Well, there's two reasons. One is, like any graph in physics, in any graph in science, it provides a visual analytical tool. We as a species are a visual species. A picture is worth 1,000 words, and seeing something graphed can help our understanding. Although we do have to be a little bit careful about that, particularly I feel in this topic, because although some graphs are very easy to interpret, other graphs, although useful if understood properly, can actually be misinterpreted very easily. So why would we draw them even if they are misinterpreted? Well, because they are very good data processing tools. You can get information from graphs. You can process it either using sort of fairly crude tools or more sophisticated analysis, but the information is still there. And when it comes to graphs there, I'm generally talking about the gradient, because the gradient of a graph will often tell you something. And the other thing that in physics we often use is the area under the graph. None of that applies just to graphs of motion, they all apply to all graphs, but very important to know why we're doing these things. So, specifically referring to graphs of motion, what are we talking about? Well, we're talking about three different types of graph: displacement time, velocity time, and acceleration time. So all these three graphs have time on the x-axis, but the y-axis varies. Now if you look at the graphs on the right, there's some three examples of the graphs there, and the first thing that you should observe is that it's pretty easy to confuse them. Okay, they can both go to positive and negative in terms of the y-axis, displacement, velocity, or acceleration. The one thing they will not generally do is go to the negative in the time axis. Although they could do, I suppose, start at a negative, because it arbitrarily decide when you want your time to start, what value of t0 you have. So to interpret the graphs, let's look at them one by one. And we'll start off with a displacement time. So the displacement, or s, is on the y-axis, t time is on the x-axis, and we'll first graph the first line that we'll examine as a horizontal line. And a horizontal line on a displacement time graph means a stationary, a non-moving object. Whereas a linear line means a constant velocity. Okay, a constant positive velocity, which might indicate increasing displacement in one direction, or a negative line, which would indicate some sort of negative velocity, maybe in the other direction. A curved line means that the velocity is increasing. It's not a constant velocity, it's an increasing velocity. If it's curved as shown in D, in other words, acceleration. Other curved lines exist, of course, but basically a flat line, a horizontal flat line, is zero velocity on displacement time graph. A linear line is a constant velocity, and a curved line means changing velocity, acceleration. Now, we've mentioned that a positive gradient means a constant velocity, so what does that actually look like? What will we use? Well, if we take the gradient is rise over run, but rise, delta s in this case, and time, delta t, so that corresponds to velocity. Velocity equals delta s over delta t. Rearranging that, delta s equals v delta t, which is an equation of the form y equals mx, which is the equation for a straight line. So, just for confirmation, the gradient of a displacement time graph gives you the velocity. If you plug the numbers in, that gradient will directly equal the velocity. And the d, the increasing gradient, means positive acceleration. So we can still use the same thing before, take 2 points, find the gradient between those 2 points, but it's not really the gradient of a line, because the line has a changing gradient, but it will give you the average velocity, and that might be enough information for you. If you want to know the velocity at a particular point in time, as shown here by t and that point on the line, then you have to draw a tangent to the line. Tangent is a straight line that touches a curve at one point only. And if you find the gradient of that tangent, that gradient will give you the instantaneous velocity. So our second type of graph is a velocity time graph. And you'll notice how very, very similar it looks to the displacement time graph. And that comes to confusion I talked about earlier. Very easy to confuse the type of graph that you're dealing with. If you're ever given one of these graphs to look at, make very, very sure you look at the axes labels and work out exactly what type of graph you have. So, A, horizontal line, in this case means constant velocity, no acceleration. And a positive gradient means a constant acceleration. So change in velocity, constant acceleration, getting faster. Negative gradient, which would generally mean getting slower, but it depends. It's up to you to define, or the question will define what is positive and what is negative. And any kind of curved line means a non-linear acceleration. Now, non-linear accelerations are, of course, exceptionally common in the real world. Almost all acceleration is non-linear, almost all. In physics, we do encounter nonlinear acceleration, but to keep life simple, so we can use certain equations that we have looked at previously and we'll look at again, then we keep the acceleration constant. Not always, but generally. Makes it life easier. So doing the analysis on that, we mentioned that a horizontal line is no acceleration, but it's true that v equals delta s over delta t, like we looked at before, so delta s equals v delta t. These two quantities, the change in velocity multiplied by the time, is like the area of a square. So if we find the area of delta v multiplied by time, in other words the area of this square, that will tell us delta s, which is the distance travelled of it, the change in displacement, strictly speaking. So the change in displacement is given by the area under a velocity time graph. Pretty easy. If it's constant velocity, it's just a rectangle like that. Still not too difficult if it's a linear or constant acceleration. Notice the terminology here, u and v and the delta t. And there's the equation just to demonstrate. So that basically says that the change in displacement is the average velocity, delta v multiplied by time taken. So mathematically, this shape here is equal to the average velocity, I guess somewhere around there, time taken. And it works also with a curve graph. Now, to actually calculate the value for a curve graph, you have two options. Option one is you use calculus. If you've done calculus in maths, fantastic. If you've not, that's not going to work for you. So the other method is a graphical method where you draw a series of rectangles and you use those rectangles, the thinner the better, although it'll take more time, to calculate the area under the graph, and then you kind of add a little bit to estimate the missing gaps. It's not perfect, but it's better than nothing. And the IB does expect you to know this and possibly use it in an exam. They may well give you a curved line and ask you to work out the area underneath it. And they won't be expecting you to use calculus. The gradient of a velocity time graph gives you the acceleration. Same reasoning as before, equation of a straight line, so gradient is acceleration. And spot the pattern there. Gradient of a displacement time graph gives you velocity, gradient of a velocity time graph gives you acceleration. And again, if you want to find the instantaneous acceleration, the acceleration at a particular point in time on a curved velocity time graph, then you'll have to choose a point, draw a tangent, and find the gradient of that tangent. Acceleration time graphs. Here's an example of an acceleration time graph. As I said, we're mostly dealing with constant acceleration. So constant acceleration will mean flat lines joined by vertical lines. So the four areas on this graph mean a positive acceleration. Then we have a negative acceleration, decreasing velocity, and then no acceleration, constant velocity for a while. and then finally a small period of increasing acceleration. Now the area under a graph is the change in velocity, just like the area under a velocity time graph was the change in displacement. And so we can use this graph to kind of work out the overall change in displacement compared to the starting position, which in this case would probably be a little bit more excess in the negative. So we'll probably start off a little further away than we started. Sorry, I got that wrong there. Change in velocity. Okay, so it's actually speeds up, slows down, stays constant, speeds up a bit. So it probably ends up going a bit slower than at the start. Let's go a couple of examples. Here's a bouncing ball. Boing, boing, boing. What was the displacement time graph looks like? Well, it'll look like this. Boing, 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 boing. A velocity time graph. Notice how this is changing its gradient. So the gradient is decreasing, 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 and suddenly increases, and then it's decreasing, 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 decreasing. Then suddenly increases, decreasing, decreasing, decreasing. So you have the velocity, but a straight velocity line means a constant acceleration. So constant acceleration, then a quick change, constant acceleration, then a quick change, constant acceleration, and a quick change. It's not intuitive. This, yes, pretty obvious. But the velocity time graph and certainly the acceleration time graph, not so obvious. But if you think about it, yeah. A falling ball has a constant acceleration, 9.8 meters per second squared. So it is constant acceleration of negative down 9.8 meters per second squared. The only time that's not true is where it bounces. Okay? Just literally in that rebound. This isn't the journey up, because from the moment it leaves the floor, it's decelerating. First of all, it's going to zero, and then going. First of all, it's going to zero, then going to zero, and then going back from zero, but it's still deceleration constant. The other example, I'm not going to go into this in any depth because we will look at this topic later when we look at waves, but it's a pendulum. And that's just to show you how kind of confusing this can be, because we have 3 examples, 3 different graphs, displacement time, velocity time, acceleration time, all describing the same object, and they all look pretty darn identical. Which is, going back to what I said earlier, if you think about this velocity time graph being a graph of a changing gradient, and the acceleration time graph being a graph in the changing gradient of the velocity time graph, kind of makes sense. So it starts off at a point of inflection, so no gradient, and then the gradient gets steeper till it reaches a maximum, and then it shallows off again to zero. So you can see how it's the same shape curve, just displaced by a certain amount, and the acceleration time graph does the same with velocity. So anyway, that's a brief look through different types of graphs of motion. Thank you very much. How do I stop this?